Hello, we are Team ScalableXplain and we will be presenting our project Explainable AI methods for distributed systems. K-means is one of the most widely used clustering algorithms for large-scale datasets. These datasets often have millions if not billions of data points with large numbers of features. Interpreting the clustering results becomes quite difficult since conventional methods such as visualizations are not possible. Let's now look into single-node IMM algorithm. Traditional clustering algorithms like K-means are good at finding clusters, but they're hard to interpret. IMM solves this by using simple decision trees, called threshold trees, to explain why each data point belongs to a certain cluster. The main idea behind IMM is mistake minimization. That means to reduce the number of mistakes, which are points far from the correct cluster center. It balances accuracy with explainability, and also provides strong performance guarantees for both K-means and K-medians objectives. Another problem with large datasets is that they are in many cases difficult to store and process in a single compute node. Distributed systems are required, and although IMM is suitable to be used in single machine settings, it is not suitable for distributed systems. So based on the above problem statement, we have defined two major research objectives. Develop a scalable and explainable XAI algorithm for K-means clustering tailored for distributed. However, applying IMM in distributed systems is challenging. To find the best thresholds, IMM needs to evaluate each feature and each possible split, checking for mistakes at every data point. This is very costly. To handle this, our approach uses two major techniques. 1. Initial candidate split calculation to lower number of unique values in threshold calculation. 2. Discretization and histogram formation for each feature to enhance calculation efficiency. Pre-processing steps for DIMM. Let's now look at the key pre-processing steps before entering the iterative mistake minimization loop. First, the input dataset, initially unclustered, must be clustered using K-means. Next, we compute candidate splits separately for each feature. These splits serve as potential thresholds for dividing the data. Each data point's feature values are assigned to bins, based on these candidate splits. The same binning process is applied to the cluster centers, ensuring consistency during comparisons in the IMM loop. Finding candidate splits. Now let's dive deeper into how candidate splits are generated. For each feature, we start by taking a sample of the dataset and compute the frequency of each unique value. We then apply quantile binning to this distribution to select split points that evenly divide the data. Additionally, we include the feature values from the cluster centers themselves as candidate splits. This ensures that the tree has splitting thresholds aligned with both the data distribution and the positions of the cluster centers. IMM iteration loop. Feature statistics. With pre-processing complete, we begin the IMM iteration loop. At each node of the tree, we must determine the best feature and split point that minimizes the number of mistakes, instances that are separated from their assigned cluster center. To do this, we collect feature bin statistics for the data points assigned to each node. For every feature, we build a histogram, the count of data points in each bin, grouped by their predicted cluster. These histograms allow us to efficiently evaluate potential splits and compute mistake counts. Histogram-based mistake calculation. This process is illustrated in the diagram on the right. At every node that is eligible for splitting, we construct separate histograms for each feature and each cluster. These histograms form the basis for mistake computation by simulating how a split would affect data cluster alignment. Using this compact representation, we can quickly identify the best split point with the fewest mistakes. Updating the tree and iterating. After evaluating all candidate splits, we select the split with the minimum number of mistakes for each node. The tree is then updated. The selected splits are applied to divide the data and cluster centers into new child nodes. Any data points that no longer share a node with their original cluster center are marked as mistakes. These invalidated points are excluded from future best split calculations. The IMM loop repeats, updating the tree iteratively, until each leaf node contains only one cluster center, marking convergence. We evaluated DIMM on 3 large datasets, US Census, SUSY, and Higgs. Tests ran on Google Cloud clusters with 2 to 8 nodes. We used 4 metrics: mistake percent, how often the explanation misclassifies points; runtime, total execution time; surrogate cost, How well the explanation mimics k-means. K-means cost, baseline clustering objective. Together, these show both accuracy and scalability. We compared IMM and DIMM on SUSY and Higgs datasets. On SUSY, DIMM had low mistake rates, around 20% on smaller subsets. On Higgs, both methods had similar performance, around 18.4%. DIMM closely matches IMM even at scale, proving strong explanation quality in distributed settings. We compared scalability using 8-node DIMM versus single-node IMM on Higgs. DIMM achieved 3.2 to 3.4x speedup on 1-5 million data points. It also kept low k-means and surrogate costs, showing it scales efficiently without losing interpretability. On the SUSY dataset, DIMM's runtime dropped significantly as we increased Spark executors. Even with 4 executors, it outperformed IMM, especially on larger datasets. This shows that DIMM benefits greatly from distributed processing. On Higgs, runtime improved steadily with more executors. At 11 million points, runtime dropped from 450 to under 150 seconds using 8 executors. This consistent trend across sizes confirms DIMM's ability to scale effectively. Explanation trees from IMM and DIMM show similar structures, same root and splits, proving that distributed execution doesn't affect interpretability. Leaf mistakes remain low, so DIMM preserves explanation quality even with parallelism. In summary, DIMM enables post-hoc explanations for k-means in distributed systems using Spark. It balances scalability and interpretability. Future work includes integrating EXKMC for more customizable, constraint-based explanations.